Hello Bobcats. In this video we will be discussing acid-base reactions, which are also a double replacement type of reaction. Now specifically the acid-base reaction we're going to look at is what's called a neutralization reaction. So it's an acid-base neutralization reaction. And what we have is that we will have an acid. So let's take an acid like hydrochloric acid, and we know that it's an acid because of the H that we see here, and so we have the acid plus we'll add a base to that. I'm going to try to color code this because later you'll see why I have acids as red and bases as blue, but our base is NaOH, sodium hydroxide, and what makes this the base is the OH minus. So whenever you see a OH minus, you know you have a base. So we have an acid plus a base, and they will react to produce water. And I'll write it as in, the HOH, so you see that this is water, HOH, liquid, and so we produce water, and it's neutral, that's why it's green in this case, and you'll also get the salt from it, in other words the sodium and the chloride, so you get NaCl, which is a salt. Now when I say salt, that's a general term for all ionic compounds. So a neutralization reaction, which is an acid-base reaction, is taking an acid plus the base, and we get a double replacement, so this positive H plus goes with this OH minus to make water, and then the sodium goes with the chloride to make the sodium chloride. And again, this is we can write this as a total ionic. So this was the formula equation. Then we have the total ionic. These are aqueous. Anything that's aqueous must dissociate. So you get H plus in solution, and I'll go ahead and say aqueous, plus Cl minus, and it's balanced. Everything in here is balanced. So 1 minus, so that's aqueous, plus sodium hydroxide is aqueous, so you get sodium ions, and these should be 1 plus, and that's aqueous, and you get OH minus ions, aqueous, and they produce water, and I'm going to write it as H2O now, which is liquid, and this is aqueous. I forgot to write aqueous up here, so that's an Na plus ion, aqueous, and a Cl minus aqueous ion. So if you notice on both sides, the chlorine is exactly the same and the sodium is exactly the same. So those are my spectator ions. And the net ionic, so my net ionic equation, which is really what's happening, is the H plus. So we have H plus. I should have used, let me try to put the color here. So I have the H plus here in red. It's not showing up. Oh well. Plus the OH minus, these are aqueous, producing H2O liquid. And this net ionic is always the same. All strong acid-base reactions make this net ionic. So this is the net ionic of strong acids, strong acid, and strong base reaction. So we're looking at a strong acid and a strong base. Always makes the same net ionic. H plus OH minus makes water. Now, we're going to talk about what is a strong acid and a strong base later, but let me review again real quick what's going on here. These are neutralization reactions, and in particular we're looking at a strong acid and a strong base. So hydrochloric acid is a strong acid, sodium hydroxide is a strong base. We know it's an acid because of this H, and we know this is a base because of the OH. And the H plus reacts with the OH minus to make HOH, or water, H2O, which is liquid. It's not aqueous, it's liquid. And the sodium plus goes with the chloride minus to make NaCl, aqueous. And then we have the total ionic here, but really what's important is that this net ionic is always the same for our acid bases. The net ionic is always H plus OH minus gives you water. Now, let's talk about some properties of acids and bases, and then we'll talk about what is a strong acid and base, and what category of acids and bases we're looking at here. So, real quick, properties of acids and bases. Now, let's start with the acids. And I'm going to do it in red, so we see that all our acids are going to be in red, and you'll see why in just a minute. So the acid properties. Acids, they taste sour. Now, don't taste an acid, but what I mean by taste sour is like weak acids, like citric acid or acetic acid. Those you do taste, because vinegar is acetic acid and they taste sour. But you don't want to taste an acid in lab. Now, acids burn on contact, so they hurt when you get them on contact. So you should wash it off right away with water, so that you minimize the amount of burning that occurs. Acids react with most metals. And you can tell that by the activity chart. If you went back to the activity chart, you notice there's only like 3 or 4 metals below hydrogen. And remember, hydrogen's the acid, and so it's only like gold, copper, silver, and platinum, I think. But everything else, all the other metals react. An acid is an increase of concentration, so it increases the concentration of H plus ions. So that's what makes it acidic. H plus in water. Now, a lot of times we don't call this H plus, we say this is a proton. In chemistry, a lot of times we say that H plus ion is a proton, because if you think about it, hydrogen is 1 proton and 1 electron. There are no neutrons. And so if you remove the electron and make it a plus hydrogen, positive charged hydrogen, what's left over is just the proton. So that's why in chemistry we tend to call that a proton. And then acids have low pHs, which means they are less than 7 on the pH scale, and they turn litmus paper red. So when you have pH paper, acids turn it red. And that's why I put all acids in red. Try to keep a cohesive or coherent color scheme here. Now bases, so let's look at bases over here. Put those in blue. Bases taste bitter. Now you don't want to taste a base in a lab, but believe it or not, all our soaps are bases, and all soaps taste bitter, don't they? They feel slippery on contact, so you really don't, it doesn't hurt, the base doesn't hurt right away. What happens is your skin starts to feel really slippery, and you realize what's going on is that the base is dissolving the proteins. And so first it just dissolves the dead skin cells. So if you wash the base away immediately, you won't hurt yourself. But if you leave it on, it's going to continue to react. Now, bases increase the concentration of OH minus in water, or hydroxide ions in water. Okay, so acids increase H plus, bases increase OH minus concentration. Bases have a high pH, meaning that their pH value is greater than 7. And bases turn litmus paper blue. And that's why I use blue for base, blue color for base. Okay, so those are some basic properties of acids and bases. Now, these acids and bases that we're talking about, there's 3 categories of acids and bases. There's what's called the Arrhenius acid base category, the Bronsted-Lowry acid base category, and the Lewis acid base. Right now in Gen Chem 1, we're just going to talk about the Arrhenius acid base category. So let's define Arrhenius acids and bases. So what makes an acid base an Arrhenius acid base? So let's look at the acids, and I'll do it in blue. So first we'll look at acids. So an Arrhenius acid is a substance that increases H plus ions when dissolved in water. So what the limit for an Arrhenius acid base is that it has to be in water. Because it's all about the increase of H plus or OH minus in water. So acids increase H plus in water. So a general equation for the dissociation of an acid is, we would say we have H being the H plus, A being the anion. When you have it in water, so when it's aqueous, it dissociates into H plus ions, and that's what increases the H plus in the water, and A minus anions. Okay, and so we'll look at strong acids and weak acids. So Here, if I have HCl and it's aqueous, and it 100% dissociates into H plus ions and Cl minus, that's the A minus, the anion. This is a strong acid, and strong acids, what makes them a strong acid is the fact that they dissociate in water 100%. So 100%, oops, it's really called ionization, not dissociation, but it's the same idea. So 100% of it ionizes into H plus and Cl minus. That's why it's so strong. Now, our weak acids, such as acetic acid, HC2, H3O2, aqueous, is, and I'm going to draw the arrows like this, and you'll understand in just a minute. So they're going back and forth, but it only slightly dissociates or ionizes into the H plus, and so and the C2 H3O2 minus ions, and so this is a weak acid. And what we mean by a weak acid is that a weak acid is or ionizes less than 1%. So there's not very much ionization going on, okay, with a weak acid. And that's why I draw this arrow. In other words, just a little bit of it goes this direction, where there's a little bit of H plus and acetate ions, but most of it exists as this molecular structure. So very little of it breaks apart or ionizes into its ions, and that's what makes it weak. Now, weak acids and strong acids, that doesn't mean that a strong acid is more dangerous than a weak acid. Not at all. Some weak acids are extremely dangerous. All that it means is that a strong acid, 100% ionization, weak acid, less than 1% ionization. Now then, let's look at the bases. So an Arrhenius base is a substance that increases the OH minus concentration when dissolved in water. So again, we're restricted to water in this case, and that's why that's what makes Arrhenius acids and bases, particularly Arrhenius acids and bases, because it's a H plus and OH minus in water. Now, the general form for this, or formula, would be MOH, where M is the metal, it's aqueous, and therefore it dissociates into the metal ion, and I'll write here metal, and the OH minus ion. And it's the OH minus that is what's important in the increasing in water. And this is what makes it basic, the OH minus. So here's my general form or formula for an Arrhenius base. Now, almost all bases are strong bases because they're ionic compounds, and ionic compounds completely dissociate. But let's go through a couple. Let's say we have NaOH. The OH is what makes it basic. It's aqueous, so that means it dissociates 100% into sodium, 1 plus ions, that's the metal, and OH, 1 minus ions. That's what makes it basic. And the other one, let's just look at one more. If we have calcium hydroxide, okay, so calcium hydroxide is aqueous, and this dissociates into Ca2 plus, remember, it's now 2 moles of OH 1 minus. So you're getting more OH 1 minus when you dissolve this in water. So that's what makes it a base. So we have the Arrhenius acid and the Arrhenius base. So let's list our strong acids and strong bases real quick, and some of our weak acids and weak bases. So there's that. Let me get a clean sheet of paper, and let's do strong acids. Now there are only 7 strong acids that you really need to know. So strong acids. And our strong acids are HCl hydrochloric acid, HBr hydrobromic acid, HI. So these are the halides. The only halide that's not a strong acid is HF. Then you have nitric acid is a strong acid. There's 7 of them, so that's 4. Then we have H2SO4 sulfuric acid. Then we have chloric acid, and the last one would be perchloric acid. Now, so there's 1, 2, 3, 4, 5, 6, 7. Now you can memorize them, but I like to know kind of why they're strong. Now these, it's easy to remember that my halides, chlorine, bromine, and iodine, are all strong, except for the fluorine. And the reason these are strong is because there's 2 more oxygens than hydrogen. So a strong acid is any acid with 2 or more oxygens than hydrogen. Makes them strong acids. So that there's 2 more oxygens than hydrogen, so it's strong. There's 2 more oxygens than hydrogen, so it's strong. Here we have 2 more oxygens than hydrogen. Here I have 3 more, so it's also strong. So those are my strong acids. What about weak acids? So really, if those are the strong, everything else is weak. But to be able to recognize a weak acid, remember my halide acids are all strong except for hydrofluoric acid. That's a weak one. Now, if we look at this, H2SO3, that is sulfurous acid, I only have 1 more oxygen than hydrogen, so it's weak. Or like phosphoric acid, H3PO4, I have 1 more oxygen than hydrogen, so it's weak acid. And then any organic acids, so, or you can say all organic acids are weak. All organic acids such as HC2H3O2. This is an acetic acid, and I know it's organic because I have a bunch of carbon and hydrogen, and of course in this case oxygen, and that makes it an organic acid. So any organic acids such as acetic acid are weak acids. So you can think of like lactic acid, tartaric acid, citric acid. Those are all organic acids. They're all weak acids. Okay, so now we've done our list for the weak, strong, and weak acids. Let's look at our strong and weak bases. So our strong bases are any thing with OH, so any M OH that is soluble. Is a strong base. So that would be like anything with group 1, so that's NaOH or Ca, calcium hydroxide, or strontium hydroxide, or potassium hydroxide. So those are all soluble OH compounds, hydroxide compounds. So they're all soluble. The weak bases, and there's only a couple that you need to be aware of. So weak bases would include insoluble hydroxides. So that are really, it's slightly soluble or insoluble. And there really is one that you need to be aware of, and that would be MgOH2. Okay? That's a weak base. And then the other main category of weak bases would be like ammonia, or anything that has NR3. It's still the same idea. This is H3, but this would be NR3. Excuse me. So, and an NR3 is, I got something in my way here. The R, in this case, R is some kind of carbon unit, okay? So, but really what's important is this one, okay? So those are our weak bases. So now you have your categories. Now there's only one other thing that I would like to address right now, and I'm going to review what a strong acid and base reaction is, and then look at a weak acid strong base. So a quick review of a strong acid base reaction. And I'm just going to use one color now. So remember, we have a strong, so let's take and look at what if we have a strong acid such as nitric acid. That's a strong acid, plus a strong base, and let's say we have potassium hydroxide. We know that's a strong base. They're aqueous, and it makes water, liquid, plus the salt, which would in this case would be potassium nitrate. Okay, and our net ionic is always, for strong acid, strong base, our net ionic is going to be H plus OH minus, both of these are aqueous, producing water, H2O liquid. Always the same net ionic when you have a strong acid, strong base. But I want to review, because I know this is in the homework, let's look at the weak acid, strong base reaction. So let's look at a weak acid, strong base reaction. Okay, so in a weak acid strong base reaction, let's take a weak acid like hydrofluoric acid is a weak acid, aqueous, plus a strong base. Let's just make it sodium hydroxide. That's a strong base. And you get water again, because remember the H plus goes with the OH minus and the Na plus goes with the F minus, plus in this case NaF, sodium fluoride, aqueous. Now there's a little bit difference in the net ionic when you have a weak, and that's because remember, these weak acids do not completely dissociate. So for the net ionic, we would write HF aqueous because it doesn't dissociate completely. But this does. And you'll notice you have a sodium on both sides, and that sodium is the spectator ion. So really, we're looking at the OH minus here because the sodium is a spectator. So on this side we have that, and then on this side the H and the OH will react a little bit, so you get your water, HOH or H2O, but over here the fluoride is the anion that is part of the net ionic. So your net ionic looks slightly different when you're doing a weak and a strong. Remember, strong is always H plus OH minus water. That's simple. But whenever you have a weak, then you have to realize that the weak on the reactant side is not completely dissociated. The strong is completely dissociated, and we're only looking at the ion that reacts, not the spectator ion, and it produces water, and then the other ion is now in solution. So it's slightly different. And I will end my acid-base reactions on that note. Have a good day.